just take your seats again. Scott, of course, is going to be around all day, so feel free to carry on any conversations with him at lunchtime and this evening at the happy hour. But in the interest of cracking on, we're going to get on to our second session today. And for those of you that were at DConf 2013, you'll have seen Maxime introducing a JIT compiler, Higgs, which I think we're going to hear more about today, and how it's progressed over the last 12 months. So, take it away, Maxime.
Okay. So I'm a PhD student at the Université de Montréal. I'm specializing in compiler design, and more specifically the optimization of dynamic programming languages. And Higgs is my experimental optimizing JIT compiler for JavaScript. So it's a testbed, a platform for me to try new ideas for dynamic language optimizations. And it has an architecture that's different from most JIT compilers out there. And the reason I'm here, if you're wondering, is that most of Higgs is written in D. And I was there last year, and when I was here last year, I spoke a little bit about the architecture of Higgs, which at the time had a pretty typical pipeline kind of architecture, where the source code gets parsed, and then we get an AST, we generate an intermediate representation, then there was an interpreter, the interpreter generates profiling data, and then there's a second level of optimization where code gets JIT compiled into x86 machine code. So the architecture has changed quite a bit since. I also told you last year a little bit about the difficulties in optimizing dynamic programming languages. And then I introduced basic block versioning, which is an optimization technique that I've been working on as part of my PhD thesis to better optimize dynamic programming languages. And finally, after that, because this is DConf, I spoke about why I chose D for Higgs, because there were other options like Go, Rust, or C++. But I ended up choosing D because I found D has a wealth of feature that's not found in all the alternatives, and also has less strange idiosyncrasies as one would find in C++, for example. And then I spoke about some of the difficulties that I had using D to implement Higgs, and in particular, a bug in the CTFE engine that caused me quite a bit of difficulty. So now I'm back this year to tell you about Higgs. Higgs has grown quite a bit since last year. Well, it's got more source code. It went from about 23,000 lines of D code to 30,000 lines. The amount of JavaScript code has almost doubled. We've got over 1,100 commits on GitHub, 215 stars. It's also much more JS compliant than it was last year. We've gotten some contributors, many bug fixes, many more unit tests. We've got an improved foreign function interface with some useful libraries to do input, output, graphics, and such things. But most importantly for my research, I have completely rewritten the JIT compilation engine for Higgs. There is no more interpreter, and I've incorporated a new architecture in there, which I call lazy incremental compilation, which I'm going to tell you more about later in this presentation. Higgs is now about 6 to 90 times faster on the benchmark than it was last year. In part, this is because I've added some optimizations like inline caching. I now have a decent register allocator in there. There's no more interpreter overheads, and the JIT compiler itself is faster, generates machine code faster than it did before. And this year, I can also show you some results for basic block versioning. So basic block versioning, last year I introduced the idea, but I didn't really have any numbers to back it up. But now I do. So basic block versioning. First, I'll start by talking about dynamic language optimization. So suppose you have a simple function like this add1 in JavaScript, which just returns n+1. Now, if we were in a static language like D, we would have to give n a type like integer, and then return n+1 is obviously just integer addition. But in JavaScript, it's not so obvious, because add1 can take any type as input. So if you had add1 of the integer 2, you'd get back the integer 3. If you did add1 of the string hello, you'd get back the string hello1. Add1 of the boolean true gives you 2. Add1 of null gives you 1. Add1 of undefined gives you not a number. add one of an object with a toString function that returns the string 3 gives you the string 31, and add one of an object with a toString function that returns the integer 3 returns the integer 4, because toString doesn't actually have to return a string in JavaScript. And of course, there's some other cases that I haven't even illustrated on this slide. So the plus operator in JavaScript has to handle all of these possible input types, have all of this logic inside of it. And at the same time, we want to make this fast as we can. So in Higgs, the less than operator would be implemented something like this. So all the operators in JavaScript are basically implemented as functions. So here we have a function less than that takes two variables x and y as inputs. And the way it's implemented internally is that it has type tests that do dynamic dispatch. So first, for example, we test if x is an integer, if it's an int32. If y is also an integer, then we can use a specialized machine instruction that does the less than integer comparison. We also want to handle the case where x and y might be floating points. And not shown on this slide, we would also want to handle a string comparison, because in JavaScript, a less than can do lexicographical ordering. And you also want to handle all of the other types that could be passed as input in there. But obviously, if we want to make this fast, we want to optimize the most common cases. And we'd like, for example, to be able, when x and y are guaranteed to be integers, to eliminate all the type tests and just have the machine instruction that does a less than integer comparison. So make it all really efficient. And the whole point of basic block versioning is to help us do that. So basic block versioning is a compilation technique that's a little bit similar to trace compilation and procedure cloning. And the idea is that as we compile, we accumulate facts. So more specifically, usually type information. When we have dynamic type tests, we can use those to gain type information. So if we test if x is an integer, we can gain the information that x is integer if the test evaluates to true, and so on. And then we use the information that we accumulate to generate more optimized machine code. And one of the key pieces is that we might compile multiple versions of the same code that are optimized based on different types. So as a simple example, if we had a little control flow graph here with just one conditional test, A, and some blocks B, C, and D. So in terms of source code, this would look something like this. So say, for example, we're testing if n is an int 32. Well, if n is in fact an int 32, if the test evaluates to true, then when we go to block B, we know this fact that n is int 32. And if it evaluates to false, then inside of block C, we know the fact that n is not n32. But what do we know in D? Well, when we arrive at the block D, we know that n is either int32 or not int32, so we actually know nothing about n. So the idea of basic block versioning is that we can basically do tail duplication based on the types. So if we duplicated the block D into two versions, D prime and D prime prime, we can separate the control flow so that we can have a block D where we know that n is int32 and one where we know that n is not int32. So as a more practical example, this is the bitwise AND benchmark from the Sun Spider suite. It's just a simple loop that does a bunch of bitwise AND operations and that increments some variable counter I. So in Higgs, we would represent the operators as functions. So we'd have a function that does the less than operation, a function to do the add, and a function to do the bitwise AND. And inside of these operators, we have type tests. So for bitwise AND, bitwise AND is typically only used on integers. So we would test if x and y are integer. And then we would have a fast pat where we use a machine bitwise AND operation that's very fast. And then if x and y are not integers, we would do a slow pat that converts x and y to int32 and then uses the machine operation. And the same thing for add, we would also check first are x and y integer, and then we would have a fast pat using the machine add instruction. With the extra complication that add in JavaScript needs to do an overflow check. So if the sum of x and y don't fit in an int32, we need to convert them to a double and redo the addition with a double, and then the result would also be a double. So if we inline all of the operators inside of our loop, we get a piece of code that's like this. So we have 6 type tests. We have a fair bit of control flow. It's a pretty bloated piece of code. So we'd like to eliminate all the type tests to have a more optimized code. So the first thing that's pretty obvious is that 600,000 and 1 are obviously int32 values. We know that because they're constants. So we can eliminate these 2 type tests right away. Then we're left with these 4 type tests that depend on the actual values of I and V. So what we do with basic block versioning is we see that I is initialized to 0, and when we enter the loop for the first time, I is an int32. So we're going to make the assumption that when we enter the loop, I is an int32. And then this allows us to eliminate this first type test and simplify the first operator to just use the machine operation. And then we see that V is also initialized to an int32 value, so we can do the same thing. We're going to assume that both I and V are int32 when we enter the loop, and then this allows us to eliminate those for type tests. And then finally, we can eliminate this other type test on I as well. And the code is much simplified. And we're pretty lucky because a bitwise AND is a machine instruction. It takes int32 values as input, and it produces an int32 as output. So we know that V remains an int32 after this operation. We're not so lucky with the add because we have that the add could actually overflow, and we haven't proved that this overflow couldn't happen. So if I plus 1 overflowed, we would have to convert I to a double, and we get a double result. And then in the second loop iteration, I wouldn't be an int32 anymore. So what do? Well, with basic block versioning, the idea is that if the overflow ever happened, which it probably won't, but if it did happen, we can generate a new version of the loop where we assume that I is a double. And then we have that at the end of the loop operation, if the overflow didn't happen, I is still int32. And then this allows us to maintain safety. And basically say that if I was ever to become a double, we would generate and jump to a different loop version that handles doubles. So basic block versioning is a bit of a multi-world approach that's different from traditional type analysis. Because traditional type analyses, what they do is a fixed point on types. So they try to find types that agree with all the possible control flow paths, and that forces them to come to a conservative answer. But with basic block versioning, we can allow multiple different solutions for the same piece of code. We don't necessarily have to sacrifice. So basically, we're doing a fixed point on the versioning of blocks instead of a fixed point on the types. Now I'm going to talk about another optimization that I've been working on, a new technique that I call lazy incremental compilation. So this is a new JIT compiler architecture that I've been developing for Higgs. That's sort of a cross between method-based and trace compilation. So it works with smaller compilation units. Instead of compiling whole methods at a time, it compiles individual basic blocks. So small chunks of code with no control flow inside. And basically, the JIT compiler interleaves compilation and execution. So it's able to compile basic blocks lazily when they're first executed. With the idea that if a piece of code is never executed, it's never compiled. And the special interest of this is that it meshes extremely well with basic block versioning because it allows us to never generate a basic block version if it won't be executed. It's hard to statically know if a basic block version would be executed or not. So if you do basic block versioning statically, you end up generating a bunch of basic block versions that don't get executed. But you want to make sure that they exist so that if they were executed, you could jump to them. But with lazy incremental compilation, we only have to generate basic block versions when they actually do occur at runtime. So as a simple example, suppose we have a function foo that takes an input variable v, and it tests if v is a number, and then tests if v is a string, and performs different operations based on the type of v. And if v is neither a number or a string, it shows an exception. So as a control flow graph, it would look something like this. So we have 2 conditional tests. But with lazy incremental compilation, we're going to assume first that none of this is compiled. And then when we have a call to foo, so suppose we have a call foo of tree, what we're first going to do is compile the entry block of foo, and then the execution will jump there. And then once we enter foo, it's obvious that we're going to need to test the type of v. We have no choice. So we're going to compile that block, and then the execution will jump there. We'll evaluate the test. And we'll see that because v is the value tree, it's a number, so the test evaluates to true. And then we compile the block that is the target of the true branch, so return, and the execution goes there. And then the return goes to the continuation of the call, so the continuation here is print x. So we're going to compile the continuation, and then the execution will jump there. And then what's interesting here is that we only compiled the part of the foo function that were actually executed. We didn't compile the second test. We didn't compile v.length, or the exception handling code. And if this was to occur inside of a loop where we would repeatedly call foo with integer values, we wouldn't recompile the code that's already compiled. So now for some results. Okay, so this is counts of dynamic type tests executed with basic block versioning with different limits of block version. So basically, I have a parameter for basic block versioning, which is the maximum number of versions that I allow for a given basic block. So here we've got max versions equals 1, so 1 version per block maximum, 2 versions, maximum 5 versions, and also no limit on the number of versions. We also have a white bar, which is a type analysis that we've decided to compare against basic block versioning to have some kind of comparison point. So as you can see, basic block versioning is able to perform pretty much always as good or better than the static type analysis. And in some cases, it performs quite well. On average, we eliminate about 60% of type tests. And this shows the proportion of blocks that have 1 version or 2 versions, 3 versions, 4 versions, 5 versions, and so on. So most blocks only end up having 1 version compiled. And this is because although JavaScript is a dynamic language, in practice, the types of variables don't change all that much. So most blocks only have 1 versions. Less than 10% of blocks end up having 2 versions, and about 0.5% of blocks have 5 versions or more. Now this is the code size growth for different block version limits. So when I explain basic block versioning to people, the first thing that they worry about is that if you're going to compile multiple versions of code, you could have a lot of code bloat. So you can end up generating a ton of machine codes. And this would really impact instruction cache performance. So this is the result for the code size increase for different block version limits. And as you can see, there isn't that much code size increase in practice. Even with no basic block version limit, the worst case that we have on those 26 benchmarks is less than 50% code size increase. And on average, the code size increases by only 4%. Now, what's interesting here, what's especially interesting, is that this is with lazy incremental compilation. Before we had lazy incremental compilation, this graph looked a little more like this. So this was back in 2013. And if we were generating the basic block versions statically, like I said, we ended up having a lot of versions that weren't executed in practice. And we had some cases where we had almost 300% code bloat. So we were able to show at the time that basic block versioning reduced the number of type tests executed a lot. So it was very effective at eliminating type tests. But because there was such a big amount of code bloat, we couldn't actually show any speed up. The code actually performed worse. So now with lazy incremental compilation, we have much less code bloat. And we're actually able to show some real measurable speed ups. So this is the execution time change for different basic block version limits relative to a baseline. So lower is better. So in most cases, we do get speed ups. We get speed ups up to about 33% in the best case. And on average, I believe it's 9% speed up on the benchmarks. So pretty good. It's not mind-blowing at this point, but I think we'll be able to improve on these results even more. So future work, there's many possible improvements and things that we could add on to basic block versioning. One of the things is I think it would be interesting to account for object property types. Right now, what I've showed you is only basically intra-procedural basic block versioning. So it accounts for the types of local variables, but it doesn't know anything about the types of the fields of objects. So I think one very interesting avenue would be to have typed object shapes. So basically hidden classes that try to account for the types of object properties. And I think this would make basic block versioning a lot more powerful and allow much speed up. So for example, it might be possible to know if you have a call to a method x.foo, you might be able to know exactly what function it's calling and not even have to look up the object field. Another avenue would be inter-procedural basic block versioning. So right now what I have, it does a lot of inlining, but it doesn't propagate types across function call boundaries. So it would be interesting to extend basic block versioning to be able to propagate types into function calls. Another interesting thing would be to do dynamic recompilation and invalidation. So with basic block versioning and incremental compilation, it's not hard to say, I want to recompile just this one block. So you can recompile a tiny part of a function dynamically without having to recompile the whole function at once. So I think that's a very interesting, powerful tool to have inside of a compiler. And finally, there's also incremental inlining. So I had a prototype of this working a while back. The idea here is that inlining functions is expensive and it's kind of time consuming in a JIT compiler because you might end up inlining a very big function and then you have to prune away the parts of the control flow graph that can't be executed in the context. So incremental inlining would be dynamically, incrementally inlining only parts of the functions that you're calling, the parts that actually do get executed, and then combining that with basic block versioning. So I think that this can make a compiler that does inlining, but does it much faster. So now, because this is DConf, I'm actually going to talk about D, and more specifically the ways in which I've used D in the implementation of Higgs. So this is basically going to be a brief tour of some of the features of D that I've used in Higgs, a collection of small use cases, things that worked well, things that worked less well, some other issues that I've encountered in the implementation. I'm going to say first, though, that I don't consider myself a D expert. I don't necessarily keep up with all the latest developments, and I'm not necessarily aware of all the best ways of applying which feature where. I come from a C++ background, and I'm still learning, picking up new tricks as I go. So there's nothing mind-blowingly clever here, and your suggestions are very much welcome on how to improve this. Okay, so Higgs needs to allocate blocks of machine code in order to generate x86 code. And so to do this, I have a class code block, and inside of it, it uses mmap to allocate a chunk of executable memory that I manage myself. And inside of the destructor, I unmap the memory that I allocated before. So I found it very useful to be able to call those POSIX functions, and that D exposes bindings to platform-specific things like that. Makes my job a lot easier. Higgs also has its own garbage collector for JavaScript object, its own allocator. So here I'm basically circumventing the garbage collector of D to allocate my own big chunk of memory that I manage myself. I did this because I wanted to be able to have very, very fast allocations. JavaScript does a lot of allocations. So I have my own specialized garbage collector just for Higgs. So the ability to circumvent the D garbage collector was also extremely useful. I'm also using memset to zero out this block. The idea here is that I want to avoid having the cost of initializing individual JavaScript objects when I allocate them. So I just zero out everything, and I made it basically so that the default uninitialized, undefined value maps to the value 0. Here, this is a struct that I use for basic block versioning in the backend. So this is how I represent values inside of my backend. And for this, I used a bit field. So D has this bit manip library that has a template for bit fields. And so I say which kind of value it is. Is it a value that's on the stack? Is it a value that's in a register? Or is it a constant? And then I have some value for the type of the value, if I know its type. A Boolean flag that tells me if I actually know what type it has or not, if the type is written on the stack. And then lastly, I have a value field which tells me if it's on the stack, which index on the stack does it have, or which register number is it in, or if it's a constant, what is the value of the constant. My one comment about bit fields, though, is that I wish it were possible to have multiple different overlapping fields with different types. Because in this case, I'm using this one field val to represent 3 different things based on the kind of value. So it would be useful to be able to say, I have a field stack index, and I have a field register number, and I have a field constant that are all superimposed, basically, as you would have in a union. Here, this is just an illustration of a place where I've used method calls without parentheses. At first I was a little reluctant, like you don't put the parentheses on function calls. You get less, visual information as a programmer as to whether it's a function call or not. But I came around eventually, and I found it very convenient to just have things that looks like it's just a flag, but it's actually a function call in there. So here I'm checking if my type operand is an immediate value, and if my output operand is a general purpose register or not. I also wanted for Higgs to have some arguments parsing. Higgs has kind of two kinds of command line arguments. It has command line arguments that go to the JIT compiler, so I can tell the JIT compiler this is the maximum number of versions that I want to have, or disable inlining. But it also has arguments to the JavaScript scripts. So maybe I want to pass some arguments to my scripts that they can evaluate. And for that, we use the double dash to separate the JIT arguments from the arguments that they get parsed to the script. What was really helpful to us is that D provides all the tools to implement this very easily. So we just use the count until function to locate the double dash, and then we separate the host arguments from the JavaScript arguments. And we pass the host arguments to a separate functions that we'll just call into the get OPT standard library. And then get OPT, we just enumerate all of our JIT arguments, and we store them all inside of a struct that we can access anywhere in the compiler. So very easy. And here, this is just an illustration of how I've used templates in Higgs. So D has a very powerful template engine, and I found it useful to be able to template machine code generation. So here, I have a function that generates RM type of x86 instructions. So there's many x86 instructions that follow the same kind of pattern. So it's useful to be able to template all those operations so I don't have to re-implement the same thing over and over and over again. So add, subtract, integer multiplication, and, or, XOR, all those instructions basically use the same pattern of code generation. And then all that I do here is that I have a mixin that will call my assembler object and call the right assembler instruction to be generated in the right place. So that worked very well. Higgs also has a bunch of unit tests. And at first, the way I implemented unit tests was with the unit test blocks. So I create a VM object. Here I'm creating a VM object that doesn't load the standard library to run some really low-level tests. And I test that some very simple expressions all evaluate to the right thing, that nothing's broken. Unfortunately, we did find that the unit test blocks were a little bit insufficient, that we couldn't assign them a name. We couldn't say specifically which unit test blocks we wanted to run or not run. And we also wanted to have a system where if someone finds a bug in Higgs, we want them to be able to just send us a pull request with a JavaScript file with some code that breaks Higgs. So we want to have a system where people could just send us a pull request with this one JavaScript file that exhibits the broken behavior that we should fix. And then the unit test would automatically get run as soon as we include it in our test directory. So what we ended up doing is we implemented our own test framework in JavaScript. And the way that it works is basically we have some functions that allow us to get the contents of the test directory. And then for all of our tests in order, we'll do a fork of the Higgs virtual machine and execute the test in a different process and then get back to results. So this allows us to initialize the Higgs VM, and then we do a fork just after the VM is initialized, so we don't have to pay the initialization cost for each VM instance. So it worked out pretty well. So this is just the tests running in order. Another thing I found useful to templates is just to have a function to access a member of an object. So there's many cases where I want to access host objects. For example, I have an object that represents a function, and I want to know how many local variables there are in there. So I want to generate some assembly code to go get me the num_locals field of the IR function class. And then I pass a register that's a pointer to my object, and I pass a register that's the destination to store the value that I just fetched into it. And then I have a second instance, so I want to access some object in the virtual machine, so vm.globalObject.word. So global object has two fields. It has a word field, that's the pointer value, and it has a type field, that's the type tag. So here I want vm.globalObject.word. The problem I had with this is that it turned out to be less clean to implement than I would have wanted. Because if you have more than one level of indirection, there is no easy way that I could find to go get the offset of words with respect to VM. You can get offset of, but that works for a.b. It doesn't work for a.b.c. And I think this would have made a good use case for having something like static for each, maybe. Because here I'm splitting the field name based on the dot operator into its different component parts. But what I end up having to do is have a specific case for x.y.z and have a different case to handle x.y. But what I would really want is to sort of just unroll the loop. I know there's a way to do it with recursion, but I think that it kind of obfuscates the code. So that was a little suboptimal. This is another strange little quirk that I ran into. So often I found that I wanted to create lists dynamically of objects. In my case, often there'll be constant values of different types. So here I have some base class A, and I have a class B and a class C that both derive from A. And I'm creating a list with a B and a C. And the problem is that I get a compiler error. It tells me that it cannot convert the expression new B of type A to type C. And it won't assign this to my list of A. But what's strange is that I said I wanted a list of A, so it should be pretty obvious how the type conversions should happen, but it doesn't happen automatically, and it's kind of unintuitive. And lastly, the biggest problem that I ran into lately is with the garbage collector performance. So I didn't realize how much of an issue this was until recently when I implemented my type analysis, and I ran into a very strange bug. So I would run my type analysis and not use the type analysis results at all. And what happened is that just running the type analysis, so the type analysis runs in isolation, it does its own thing. And then I execute my program, and the speed of the execution of the program would slow down a lot just by running the type analysis. And I wasn't counting the time taken by a type analysis, so I didn't understand how running this thing in the same process can slow down another thing afterwards in the same process. What's the link between the two? At first I thought maybe the type analysis is trashing the cache. Or maybe there's too many context swaps, so I wasn't sure. But eventually I tracked it down to the garbage collector. So the type analysis allocates quite a bit of memory, and that tends to fill up the heap. And then when the heap is more full, garbage collections happen more frequently. So what I did is I looked more into it, but then eventually I also noticed that just allocating more data makes the allocations themselves quite a bit slower. So I can pre-reserve a big chunk of memory so that allocations don't happen more often, but having more data that's been allocated makes the speed of memory allocations much slower as well. So what I did was I pre-reserved a big chunk, a gig of memory, and this produced a speed up of 2x on some of my benchmarks. And then I tried making less allocations. I didn't think I was using the GC and allocations that much, but I tracked down the places where I was doing allocations, and I eliminated most of them, and I found out that I got another 2x speed up again on some benchmarks. That really surprised me. But it makes me think that probably the biggest bottleneck in Higgs right now is the D garbage collector. That's probably the biggest reason why the compilation time isn't so great. And I think that the traditional systems programmer response to this would be, well, you're doing too many allocations. You should do less allocations. But for me, that's kind of sad, because if I do less allocations, it means my code is less maintainable. I have to refactor my code to embed some objects into other objects and do all kinds of maneuvers and have allocation pools. But that adds a lot of overhead if I want to refactor my compiler later. And compilers kind of need to be able to do allocations to do symbolic transformations. So I had a friend do a benchmark. I wanted to know how slow is the D memory allocation in garbage collectors. I had this friend run the same benchmark in D and Java. So maybe you'll think that's not a fair test, because Java has different semantics. It's not the same language. But I know they've put a lot of effort into engineering a very efficient memory allocator in garbage collector. And here we have a test where every 9 iterations, it's allocating arrays of different sizes, and it increases the maximum size of the arrays it's allocating. And as we can see, the Java allocator in garbage collector is several times faster than D's. So I think that, this is a little bit embarrassing. But it shows that there's room for improvement. I think that the D memory allocation performance could be improved quite a bit, and that this would make D a lot more appealing for some kinds of applications. And I'd like to conclude by my own perspective as someone who's maybe less involved in the D community. I feel like a lot of people here spend a lot of time on the D forums, and you guys are really up to date on all the latest developments and everything that's happening. But as someone who doesn't go into D forums that often, I mostly go when I have a problem and I'm looking for a solution. I find I'm not aware of all the best ways to use different D features, and I'm too lazy to go and do a lot of Googling to really inform myself about D. And I think that's a problem. People are lazy, and you might not realize how lazy they are. Just as an example, we had a problem with Higgs that we didn't know about until recently. So I develop on Linux, and my friend Tommy, who's helping me on Higgs, also develops on Linux. And we know that a lot of people downloaded Higgs, and forked it and tried it and all that. But until recently, we weren't aware that Higgs didn't work on OS X. It crashed. There was a bug, something that we needed to fix, but we never tested Higgs on OS X. We just assumed that people would have told us. And we know that dozens and dozens of people tried Higgs, and probably at least half of those people were on Mac and encountered this problem. But nobody told us until we got chatting on our chat room with some people that had been in our chat room for several weeks. And we started chatting with them more, and at some point somebody said, well, it doesn't work on OS X. So I think this just goes to show people are lazy, and they won't necessarily tell you about your problems and all that. And I think in terms of learning D, maybe there should be more effort made to lower the bar, to make it easier for people to learn about it. And my personal recommendation would be to make more room for tutorials on dlang.org. Focus on examples, maybe short bite-sized pieces of idiomatic code, clever snippets, things that make D stand apart, things that would maybe interest someone like me who comes from a C++ background. Like the for each loop. I think the for each loop is one of the cool things that D has that C++ didn't have a while back. You should have little snippets that illustrate all these cool features, and maybe every time someone goes on dlang.org, they should see a different snippet of code. Just a different bite-sized piece or something. So that would be my advice. Make the tutorials easier to find, give them more space on dlang.org, make them more obvious. And this concludes my talk for today.
I found it very interesting that you compiled the basic blocks independently of each other. I presume that means that they're connected by jumps from one to the next?
Not necessarily. In many cases, we find that there's a little bit of clever design that goes into this, but basically we're able to compile the blocks all in sequence, and if they come all after one another, if we're just going through like a straight line path, we don't have to put jumps from the current block to just the immediately next byte. So we're able to avoid a lot of these jumps.
Because I was going to suggest One thing I've noticed, because of CPU caching, if you have functions that call each other strongly, if you locate them next to each other in memory, you can get dramatic speed improvement. So I was just wondering if you did that for your JIT, because you have a runtime graph of how often the things are called, and so you can sort of sort the functions in memory.
Well, right now
get better performance.
I don't pay specific attention to that, but it does happen in a way that if you have a function foo that calls bar and bar hasn't been compiled yet, then from the call site to bar will be compiled immediately next to the call site. So they will be automatically located close to each other. But of course, that only works if you have a function that's called from very few places or just from one caller. There is one cool thing that I want to integrate into this eventually, though, is to have a reordering, like a garbage collection and compaction of the compiled code. So I've done it in a way that I can relocate all of the code that I've compiled, and I can eliminate the dead code. So eventually I can copy all of the machine code and reorder everything to just make it more optimal.
Okay.
Hi, you were saying that there were a lot of allocations you didn't expect. I was just wondering where those allocations were, if it's just the usual suspects like array appends and stuff like that, or if anything weirder.
I wouldn't say that there were so much allocations that I didn't expect. My code does some allocations when it executes. There are a few instructions that we're calling back into the host code. And for example, I was allocating temporary D strings. And I thought that this wouldn't matter at all for performance, because it doesn't matter if like a few times during execution I go and allocate a D string. But it turned out to be a big performance bottleneck because the allocations themselves were very slow. And sometimes I would trigger the garbage collector during execution, and that would also lead to a huge slowdown.
So it's literally as simple as just using a few strings here and there.
Yeah, just allocating a few strings during execution was a huge problem. And I posted on forums about this. What I ended up doing is creating my own string object that's just a slice of an object inside of my JavaScript heap and referencing to those bytes directly. And that's a little risky because if my garbage collector is triggered, that view is going to be invalidated. But for some very narrow specific cases, it works well enough.
Okay, thanks.
Let's see, I was just wondering whether you ever tried doing a source code translation from JavaScript into D, because there is the variant type within the standard library. I'd just be wondering how the two would compare your just-in-time compiler versus a translation.
I mean, compiling JavaScript code into D code? Mm-hmm. I think that could be made to work for some cases. With type inference, I think it could actually work pretty well. The main problem with that sort of thing, though, is that you can't so much do load and eval. You're a little bit more restricted in terms of dynamic behavior.
All right. We don't have any more questions off the live stream, but there are plenty of people saying it was an awesome talk. So
thank you very much.
Congratulations, and thank you very much indeed. And we'll be back at 11 for the next talk.